This lesson explains why a filtered DC supply, as it is, may still be unsuitable for sensitive electronic circuits. We will define line regulation and load regulation, interpret the common units, and then apply those ideas to a simple Zener diode shunt regulator. The final section develops a complete design and checks the Zener and resistor power ratings. By the end of the lesson, you should be able to distinguish line regulation from load regulation and calculate both. You should also be able to explain why a reverse-biased Zener diode can serve as a voltage reference, calculate the series resistor, determine Zener current under limiting conditions, and select practical power ratings. A rectifier and filter produce a reasonably smooth DC voltage, but smooth does not mean constant. The output can change when the mains voltage changes, when the load draws a different current, because residual ripple remains, or because component parameters change with temperature. A regulator is therefore placed after the filter to oppose these variations. Follow the power flow from left to right. The transformer provides isolation and the required voltage level. The rectifier converts AC to pulsating DC, and the filter reduces ripple. The regulator then receives an unregulated DC input and produces a more stable voltage for the load. The regulator cannot create energy, it controls voltage by absorbing or redirecting changes. For disturbances are especially important. Line variation changes the filtered input presented to the regulator. Load variation changes current and therefore internal voltage drops. Ripple is the residual periodic variation from rectification and filtering. Temperature changes diode voltage, resistance, gain, and reference values. Regulation is the ability to limit the resulting output change. A fair regulation test changes only one independent quantity at a time. For line regulation, vary the input voltage while holding load current and temperature constant. For load regulation, vary the load current while holding input voltage and temperature constant. If several quantities change together, the measured output change cannot be attributed to one cause. Line regulation is the output voltage change divided by the input voltage change. Delta VO is the output change, and delta VI is the input change. A smaller value means the regulator rejects input variation more effectively. When the result is stated in millivolts per volt, it tells us how many millivolts the output moves for each 1 volt input change. The output rises from 5.02 volts to 5.08 volts, so delta VO is 0.06 volt. The input rises from 12 to 15 volts, so delta VI is 3 volts. Dividing gives 0.020 volt per volt, or 20 millivolts per volt. The load current is unchanged, so this is a line regulation result. Load regulation measures the output change when load current changes. The ratio delta VO over delta IL has units of ohms and behaves like an effective output resistance. A smaller value means the supply is stiffer. Percentage load regulation commonly compares the no-load voltage, VNL, with the full load voltage, VFL. At no load the supply gives 5.05 volts, and at 100 mA it gives 4.92 volts. The output change is 0.13 volt. Dividing by 0.100 ampere gives an effective output resistance of 1.3 ohms. Dividing the same voltage change by the full load voltage and multiplying by 100 gives 2.64%. The regulator acts as a control element. If its input rises, it must absorb more voltage internally. If the input falls, it must reduce the internal drop, provided enough headroom remains. When load current rises, the regulator supplies the extra current while limiting output fall. When load current falls, it diverts or reduces the excess. A Zener diode is designed for safe operation in reverse breakdown. Near the specified Zener voltage, current can change substantially while voltage changes only slightly. The voltage is specified at a stated test current. Useful regulation requires current above the knee region, while the maximum current is limited by the diode power rating. The Zener voltage is not perfectly constant. The device must carry enough current to remain beyond the knee, but not so much that its power rating is exceeded. Zener power is Vz times Iz. An approximate maximum current is the maximum rated power divided by the Zener voltage. Datasheet tolerance and temperature also affect the actual voltage. The series resistor R sub S limits current from the unregulated supply. The reverse-biased Zener diode is connected across the load RL, so the output is approximately the Zener voltage. Because the Zener and load share the same two nodes, they have the same voltage. The incoming current divides between the load and the Zener. Start with the approximate voltage relation, VO is approximately Vz. Ohm's law gives the series current as Vs minus Vz, divided by Rs. Kirchhoff's current law then gives Is equals Iz plus IL. Finally, the load current is Vz divided by RL. The key regulating action is current redistribution. If the supply rises, series current rises and most of the extra current flows through the Zener. If load current rises at fixed supply voltage, Zener current falls by approximately the same amount. Regulation continues only while the Zener current remains within its useful breakdown range. Design must satisfy two opposing worst cases. At minimum input and maximum load, the resistor must be small enough to leave the required minimum Zener current. At maximum input and minimum load, the resistor must limit Zener current and component power. A design based only on nominal input can fail at either extreme. At the low input, high load condition, calculate the maximum allowable series resistance. Choose an available value no larger than this result. Then calculate the maximum Zener current at high input and minimum load. Finally, check Zener power and resistor power. These equations keep the design tied to the actual limiting conditions. The design uses a 10-volt Zener diode. The unregulated supply ranges from 15 to 20 volts, the load is 1 kiloohm, and at least 5 mA of Zener current is required. We must select the series resistor and suitable minimum power ratings for both the resistor and Zener diode. The load current is 10 volts divided by 1 kiloohm, which is 10 mA. At minimum input, the resistor must supply 10 mA to the load plus at least 5 mA to the Zener. The maximum allowed resistance is therefore 333 ohms. Choose the next lower common value, 330 ohms. Now verify the chosen 330 ohm resistor at the low input condition. The series current is 5 volts divided by 330 ohms. Subtracting the 10 mA per load current gives a Zener current of about 5.15 mA. This is slightly above the required minimum, so regulation is maintained under the stated condition. At 20 volts input, the series current rises. With the 10 mA per load still connected, the Zener current is about 20.3 mA. Zener power is 0.203 watt. Resistor power is about 0.303 watt. Ratings must exceed these calculated values and should include reasonable design margin. A practical selection is a 330 ohm, half-watt resistor and a 10-volt Zener rated at least half a watt. These ratings exceed the calculated dissipation. If the load can be disconnected, all series current flows through the Zener, so the no-load case must also be checked before finalizing the design. A real Zener characteristic is not perfectly vertical. Its slope is represented by dynamic resistance, Rz. For a small current change, the output change is approximately Rz times delta Iz. With a fixed load, the small signal output resistance is approximately Rz in parallel with RL. Lower dynamic resistance improves regulation. The Zener shunt regulator is simple, but efficiency can be poor because current continues through the Zener even when the load needs little current. Regulation is lost below the knee. High input or light load can raise dissipation. Tolerance and temperature cause voltage error. The circuit is therefore most suitable for low power loads and modest input ranges. For errors recur. Designing only at nominal input misses the worst cases. Ignoring load current violates Kirchhoff's current law. Checking Zener power but not resistor power leaves a thermal risk. Finally, assuming an exact output voltage ignores tolerance, dynamic resistance, and temperature. A disciplined worst-case calculation avoids these mistakes. The central ideas are these. Regulation limits output change. Line and load tests isolate different disturbances. A reverse-biased Zener can hold the output near its breakdown voltage. The series resistor both supplies the load and limits Zener current. A valid design checks low input with high load, high input with light load, and the power dissipation of every stressed component. Use these questions to check your understanding. First, calculate effective output resistance and percentage load regulation. Second, express a measured line regulation result in millivolts per volt. Third, apply Ohm's law and Kirchhoff's current law to determine the three currents in a Zener regulator. State the control variables and units in every answer. A regulator completes the basic DC power supply chain by stabilizing the filtered output before it reaches the load. The Zener shunt regulator is an excellent first model because it makes line, load, current division, and power limits visible. In practice, select the regulator topology that meets the required current, accuracy, efficiency, thermal, and safety constraints. Never connect this low-voltage circuit directly to the AC mains.